Students, today our topic is potentiometer, and it is a very useful device for finding the very small voltages and EMF of a very small cell. So this device works on a basic principle that whenever in a circuit, if we have a battery and we connect across it some resistance, then the potential, say we give it a 5 volt potential, this potential gives rise to some current through the resistance, and when the current passes through this resistance, this potential which was applied, it is somewhat decreased across it. How? As we know, the potential difference V is equal to IR. So basically, when current capital I or some current capital I passes through the resistance having resistance capital R, then this much potential is developed across the ends of this resistance. Any device you use in your household or in some lab, they all have some resistance. Therefore, whenever we connect a device or some resistance or some conductor across a battery, its potential difference which it is applying, it is decreased by some value. However, the current through the circuit remains same as they are in series. So this basic principle is applied in this potentiometer. So now let's start with the construction, its principle, and how we can use a potentiometer to find a potential difference. Students, as we can see here, I have constructed a potentiometer circuit. In this diagram, we start from this part. First of all, there is a rheostat. The rheostat, you know, this is a device which can provide the value of resistance you want. So it is different from the normal resistance box in respect that it has a very long wire, and whichever value you want in the circuit for the resistance, you can include that value. Now, this rheostat is connected to an ammeter which will obviously note the current through the circuit, and we have marked it as A1. So this is the positive end and this is the negative end, as we have connected a battery of EMF E in the circuit, and this circuit is termed as auxiliary circuit. Why it is known so? Because of this, the current flows through the circuit. So our main part for the potentiometer is this. The potentiometer wire is made up generally of manganese or constantan. These are the materials which have a very low coefficient of temperature for resistance. That means for these type of materials, the resistance do not change very abruptly with the rise of temperature. As we know, whenever we run a circuit, the temperature of the wire or the conductor that rises. So this is the starting point. From here to this point, these are the carbon strips, and a wire of length 100 centimeter or simply 1 meter is connected across this. Then again, there is again a copper strip here. We have used the copper strip to join these wires because the copper is one of the good conductors and it is readily available. So on reaching here, again a wire of same material is connected, and its length is also 100, so it makes 100 plus 100, that means 200 centimeter. again a copper strip, then again 100 centimeter length of wire, again a copper strip, and again 100 centimeter length of wire. So what you get a 400 centimeter long wire across which you can find the potential difference. So now, as we know that even a small length of a conductor that offers some resistance to the flow of current. So obviously by setting up some resistance from this rheostat, we can assume some current to be flowing through the circuit. Now at this point the potential difference will be the maximum as it is coming from the battery, and there is no resistance that has been connected across this battery up to this point. But after this, if we take this point as initial point where the whole of the potential difference of the battery or simply the total current is coming, then from this point now on, further moving to this or this or this, wherever we go, we assume a length of the wire in the circuit, and obviously as I have explained earlier, there will be some potential difference across each part of the wire. So if I consider this part up to this length, say I take a point C here, then this length of the wire will have some potential difference across it, and what we will get if I have applied say 10 volt of the potential difference through the battery, then some of the potential difference will be there and remaining will occur across the remaining part. Therefore I can check the potential difference at every point by the use of a jockey and a voltmeter, that how much potential difference has developed across the given length. Now on increasing the length, what will happen? The potential difference across the wire will increase, or simply in other words we can say the potential drop across the potentiometer wire will increase, and ultimately on increasing the length we may find some point at which whole of the potential difference applied by the battery is dropped and you get a 0 volt voltmeter reading. That means we can get the resistance from that much length of the wire for which the potential difference or potential drop is same as provided by the battery. So this is the basic principle of potentiometer, that whenever we apply some potential difference across a resistance or a length, then some length of the given wire may offer the same potential drop as is provided by the battery, and thus we can say that the basic principle of potentiometer is can be termed as resistance offered by the potentiometer wire is directly proportional to the length of the wire. So now let's see mathematically how we can drive this relation. So let capital R be the resistance of length AJ of potentiometer wire of length, say we take its length L, having area of cross section capital A and resistivity rho. So these are the parameters we are taking into account. As we know the relation between the resistivity, length, area and the resistance of the conductor, so we can write it as capital R is equal to rho L upon A. This is the value of resistance of the potentiometer wire. If I assume that the potential difference across the total length L of the potentiometer wire is capital V, then V must be equal to IR using Ohm's law. Now putting this value of R in this equation, we get V is equal to IL rho upon A. From this relation we can see that this rho resistivity, this is a microscopic property of the conductor which remains constant, and this capital area of cross section of the potentiometer wire, it is also constant, and by the use of rheostat and this arrangement we have assumed that the current through the circuit remains same, that is capital I. Therefore V is proportional to, we can readily say V is proportional to, by taking this capital I, rho and capital A as constants, we can take V proportional to L, or we can write V is equal to capital K into L, where capital K is nothing but this I rho upon A, and this term, this capital K, is also termed as potentiometer constant or potential gradient across the wire is termed as K is equal to V upon L. Remember, we have learned earlier that whenever we divide a quantity with a length of a substance or some distance, that becomes a gradient. So what you get, potential divided by length, that means potential gradient, which is equal to K. So remember this term. So what you get this principle that whenever you attach some potentiometer with some arrangement for which you are calculating the potential difference, then you calculate the length for which this voltmeter shows no deflection. So for that we can say the potential difference provided to the potentiometer is equal to K times the length it acquired on the potentiometer arrangement. The next subtopic in the topic of potentiometer is the applications of potentiometer. Remember, generally for our convenience we take a potentiometer of a length of wire 100 centimeter only, but whenever we need a potentiometer of 400 centimeter length wire, we can use that also. However, generally the circuits where the potential differences are not very large, we only use the potentiometer of length 100 centimeter. Students, as I have mentioned before, the main use of potentiometer is where there is very small potential difference. Now we consider the case of a cell in which we have to find the EMF. As we know by the definition of EMF of a cell, that it is the potential difference between the two terminals of the cell when no current is drawn from the cell. So this is an obstruction in calculating the potential difference or the EMF of the cell by using the Western type galvanometer, because it acquires some of the current from the cell. So if you start finding the value of EMF by using Western time galvanometer, then that value of EMF will not be correct. We need an arrangement which takes no current from the device and provides the correct potential difference. So for that we use the potential difference, potentiometer. Now we use potentiometer. Now on the basis of this, we have the first application of potentiometer, that is the comparison of EMFs of two cells using the potentiometer. So students, this is the circuit for calculating or comparison of EMFs of two cells. In this problem, what we consider is we have a cell, say E1 is its potential or EMF, and we know this value. There is another cell for which we assume that its EMF is E2, and now we have to calculate the value of E2 using this E1. Now let's see how we can calculate this value. Now first of all, as by the construction of the potentiometer, we can see that there is this circuit containing a battery of say EMF or terminal potential difference E. This is the ammeter and this is your rheostat. I can write it like this. And there is some key K which is closed. So this circuit is termed as auxiliary circuit. As I have mentioned in the previous topic, this is the auxiliary circuit by which the current flows through the circuit. Here what we have considered a potentiometer of length 100 centimeter wire. Why? Because here the potential difference to be measured is assumed to be very small. Now in this arrangement we have connected the two cells, one for which we know the potential difference or EMF, and the second for which we have to find the EMF, and they are connected to point A. Here there is a two-way key. Two-way key means whichever side you want to connect, you can connect. You may connect to this end 1 to 3 or 3 to 2. So whichever side you want to connect the first cell with EMF E1, you can connect that, or simply the other cell. Then after this there is galvanometer and a jockey connected to that. Now what we do is, first of all we connect this point to point 1. That means we include this cell of EMF E for which we know the value of EMF, and we get some reading. Say I connected this and I started the jockey and moving this in this side. So going in this side we get some point, say J1. This is the position of jockey for which the galvanometer shows no deflection. That means we have find a balanced point. Now by the use of potentiometer principle, that for this length, say this length is L1, we can write the potential difference as we have provided the potential difference E1 here. So this is equal to K times L1. We have considered this length J1 is equal to L. So we get this equation. Remember, the only potential difference which comes in this circuit is this, not this one, because it provides the current only. Okay. So you get E1 is equal to KL1. Similarly, if I detach this and now connect it to the terminal 2, we have included the other cell with EMF E2 in the circuit and removed the first cell. Obviously, as it may have EMF different from the first cell, therefore we may get some other length up to point J2, which is the next position of the jockey. Then for this we have E2 is equal to KL2. We get the two equations. Remember that the potentiometer constant is same in both the cases, but the lengths are different. Now simply divide these equations. Dividing equation 2 by equation 1. So what you get? E2 upon E1, this is equal to KL2 upon KL1. So this K cancels, and what you get? We get E2 is equal to E1 L2 upon L1. So this is the relation from which we can find the unknown EMF of a given cell. Or simply, if you have to compare the EMFs, if you don't know the values of EMF of both the cells, then from this relation we can find that which cell has the larger EMF and which have to be used. So students, this was the first application. Students, our next application of potentiometer is to find the internal resistance of a cell using the potentiometer. Here, this is the circuit for finding this. We have again considered a potentiometer of length 100 centimeter. Here we have just changed this applied voltage or battery voltage to be V. And in this circuit, from A to B, we have connected a cell of EMF E. This cell is also connected to this circuit, this external circuit, in which there is a resistance box and there is key K1. First of all, we take it as in the open position. That means in the open key arrangement, this circuit will not be considered, as there will be no potential drop from this cell across this circuit. Therefore, we don't take this in the open key arrangement. Now let's see what will happen. Obviously, when this is not connected, we will get some value of the length of the potentiometer wire, for which the galvanometer shows no deflection, and let that length of the potentiometer wire is L1. So by the principle of potentiometer, we have E is equal to K into L1. This is the value of EMF of the cell, which we obviously know. Now, if I put the key here and close this key, now some of the current will be drawn from this cell of EMF E, and obviously by the definition of terminal potential difference, when we connect a cell across a circuit and the circuit draws some current from the cell, then the EMF of the cell is termed as terminal potential difference, and it is always less than the EMF of the cell. So when we put some resistance and close this key K1, and now if we find the length, this length of the wire of potentiometer for which the balance point is occurring is obviously less than the first case. So we get the terminal potential difference as KL2 by the use of potentiometer principle, and obviously dividing equation 1 by 2, we get E by V is equal to KL1 by KL2. This is equal to L1 by L2. So we get the ratio of the EMF of the cell and its terminal potential difference in terms of lengths of the potentiometer wire. So now the internal resistance in your article of cell, its EMF, we have already discussed the internal resistance say R, that is termed as E by V minus 1 into capital R. So this is the value of internal resistance. So here what we need the value of capital E by V, and we got this value here. Sorry, this will be equation number 3. Now put this value of E by V in this equation, and what you get R is equal to L1 by L2 minus 1 into capital R. Capital R is the value of this resistance which you have included. So by using this formula you can calculate the internal resistance of the cell. I hope the potentiometer principle, its construction and its two applications which are most important for the examination point of view are now clear to you. And if you have any query or any doubt regarding this lecture, you can comment me in the comment box. I will always answer your queries. Thank you. Please like and subscribe my channel and share it with other